So this is where we're going to go with this. We're going to start talking about subtractions now. Additions were quite alright. Let's start with how do we actually do long subtraction. Now, I usually get it wrong, so once again, raise your hand if you see me do mistakes here. 9 from 0. Let's have a look at here. 0 minus 9, we can do it. We borrow a 1, so this becomes a 2. 10 minus 9 is 1. I'm not going to be as fast as him. Then we have 2 minus 1 is a 1. And we get 11, which is hopefully the right answer. So far easy. What about the other case? 19 minus 30. Well, 9 minus 0, 9. 1 minus 3, well, we can do 1 minus 3, so we borrow a 1 from thin air. 11 minus 3 is 8, and we get 89. What? Obviously, clearly not quite the right answer. What should be the right answer? Minus 11, yeah? How do we get minus 11 from this? And then
minus 1 and you put 30 over 19 and you get 11 and you do minus 1.
Right. How about we'll apply a correction step and we'll take 100 minus that 89, and the 100 came from thin air again. I will explain where it comes from in a second. We will get 11. So that's the magnitude of the result we're after, but we really want negative 11. So we'll add a minus sign, and we end up with the correct result after we apply this correction step there. And we can do the same thing in binary, and these are the very same numbers that I used before. If I try to do the binary subtraction, and this is where it starts getting a bit messy, 0 minus 1, well, we can't do a 0 minus 1, so we have to borrow a 1 from the next stage. 2 minus 1, so this is now a 2, is a 1. Now we have 0 minus 1, well, we can't do it, so we have to borrow from the next stage. 2 minus 1 is a 1. Next stage, 0 minus 0 is 0, no problems. 1 minus 0, 1. 1 minus 1 is a 0. And hopefully this is the correct answer. Is this 11? These are the same numbers, by the way, in binary. So, is this 11 in binary? Yes? Good. Now let's try the other way. 1 minus 0, 1, 1 minus 1, 0, 0 minus 1. Well, we'll have to borrow, but we can't borrow from here. So we'll borrow from here. It'll be a 0. This will be a 2. 2 minus 1 is 1. 1 minus 1, 0. 0 minus 1, well, we're going to have to borrow from somewhere. And then 2 minus 1 is a 1. Everyone's following me? Clearly, that's not minus 11. In fact, how do we even write minus in binary? We haven't talked about it. If we try to add the minus sign at the beginning, that's not going to be minus 11. But let's see if the same trick of the correction step will work here as well. So we'll take 1 and 5 zeros. The zeros correspond to how many bits I've got there. Minus 1, 0, 1, 0, 1. Clearly there's going to be a whole lot of borrowing here. So I will need to borrow from everywhere. So all of these will now be borrowed. This will be a 2. 2 minus 1 is a 1. 1 minus 0 is a 1. 1 minus 1 is a 0. 1 minus 0 is a 1. 1 minus 1 is a 0. And this is pretty similar to what I've got there, but I need to add a minus sign to it because I applied the correction step. Still sounded a little bit dodgy, yeah, question?
Could you explain again when there's going to be a 2?
All right. Long subtraction, right? So we had a 0 here. We had to borrow a 1 from the next power of 2, right? So this is 2 to the power of 1, so we're sort of borrowing a 2. This will be a 2. Yeah, because we're not changing the values of the numbers that we use, we just shift them around. Yeah? So we borrowed a 1 from here, so this will now be a 2, because this is the 2's place. 2 minus 1 is this. Now, this didn't have anything to give us, so we had to keep borrowing. When we borrowed, this was then sort of a 2 from the next stage, if you want. But we borrowed 1, so 2 minus 1 is 1, and only left us with this 1. I told you you'll play with your head. In a way, it's very similar. In fact, it's identical to decimal subtraction. If you can do, if always you're in doubt, go back to the decimal subtraction, if you remember this from, I don't know, 4th grade. Is it 4th grade? Anybody remember when we learned about this? So the same ideas go there. But here's a hint, a clue. Don't worry too much about it just yet, because what I really want to show you is that how much it plays with your head, and then how simple I can make things later. So if it plays with your head, I got my mission done. Now to formalize what I've actually done before, so I will start using letters M and N. So I'm taking M minus N. M minus N. So I'm subtracting, oh, you can't see it there. M minus N. Now if M is larger than N, then I get a result and I don't have any borrow or an N bar coming from the left. Right? The top number is larger than the bottom one. I am expecting to get the right result. I won't need to borrow anything from thin air. It's all good. So that's not a problem. The problem starts if N is actually larger than M. And as we saw what we've done, we sort of had to borrow 1 from thin air. In fact, what we've actually done is add 2 to the power of N to the whole number. And in fact, what we've done M minus N, where N is actually larger than M in this case, and we added the number 2 to the power of N from thin air. That's what it meant to borrow that 1 in the nth position. So then, to get the right result, I will then, if I had to borrow this 1, I will subtract the 2 to the power of N from the number, which is what I've done here. Sorry. I will subtract the number from 2 to the power of N, like I've done there. And then I will apply a minus sign, because this is a correction step, and I know that N was larger than M, if I had a bar. Now when I do, when I then subtract 2 to the power of N minus the operation that I've done, I do get 2 to the power of N minus this number here, which is M minus N plus 2 to the power of N, which is the same as N minus M, correct? Which is why I then need to put the minus sign in the correction step. Now, when I do something like 2 to the power of n minus a number, and this is not the same n as before, it's a new number. Chris, can you please shut down your laptop? Thank you very much. Everyone behind you is looking into your laptop rather than n and m here. So, when you do 2 to the power of n minus some number, that's called taking the 2's complement of n, and we'll talk more about complements in a couple of slides' time. Now, if we wanted to design a circuit that does both addition and subtraction, we will end up with something that looks like that. So we had the binary adder, which we designed in the previous hour. Takes A and B, no problem. We'll have a binary subtractor circuit that will take the A and the B. Now we don't know which one of them is larger than the other. This will have an output, a borrow output, that will tell us whether we needed to borrow something from thin air. If this is asserted, then we know we have to apply a correction step, and this is what this block here will do. If there was a bar, then this will take the 2's complement, or do the 2 to the power of n minus the result there. Stick a minus sign. Somehow, we still don't know how we are representing minuses in computers. And we'll push the result out. Now, this whole circuit can be used both for addition and subtraction. In order to, choose what we want out of the circuit, we have a subtract or add signal coming in to this multiplexer. And this will choose, if this signal is 1, then it will be a subtraction. If it's a 0, it will be an addition, and it will choose which one of them comes out. By the way, this is a bit of a notation, something slash something with a bar, meaning if it's true, then this will be the signal. If it's false, this will be the operation. So you might see this in data sheets as well, this type of notation. That's quite a complex circuit, the whole thing there. There's got to be a better way to do it. And the way we're going to go about doing this is to introduce complements as an approach to do these kind of things. So what are complements? And please note, it's complements, not complements. It's not, oh, what a pretty number you've got there. Nothing like that. It's complements. So there's two types of complements we'll talk about. There's the diminished radix complement. And this is true for any base that you're working with. And this will be called the R-1's complement. For example, R being the radix or the base. If I'm working in base 10, then R-1 will be 9. So I will call it 9's complement of a number. And it's defined to be R, which is the base, to the power of n, which is the number of digits we have in a number, minus 1 minus the number. And this is just the definition of what the R-1's complement of a number is. We can also take the R's complement of a number, which is defined as R to the power of n, small n being the number of digits, minus the actual number. If you worked in base 10, this will be the 10's complement of the number. But because we usually work in base 2, in binary, these two things will become 1's complement and 2's complement, respectively. And these are the concepts that the 1's complement and the 2's complement that we'll be using most. Now let me give you examples of how we come up with the 1's complement and the 2's complement. So for example, R is 2, so base 2, we're working in a binary. we have an 8 bits number that is this number here. We want to take the ones complement of this number. So the definition was r to the power of n, which is n is 8, the number of digits, minus 1. So you'll be 1 and 8 zeros minus 1, which is just 8 ones. And then we subtract the number large N from the string of ones. So 1 minus 1 is 0, 1 minus 1 is 0, 1 minus 0 is 1, 1 minus 0 is 1, 0, 0, 0, and 1. Fairly simple, but it can be even simpler. If you realize taking the ones complement essentially means inverting all the bits in the number. Is this a nice drawing that you put there? Did you write something? Can I see it? You want to show the whole class?
It's actually a very nice drawing. Sorry.
Bring it on. I've got a camera. The ones complement of a number, the easiest way to find it, invert all the bits in the number. And you can prove it to yourself that this number is just the original number, all the bits inverted. So whenever you're asked to take the ones complement, don't, it's the easiest thing ever, invert all the bits. How about two's complement, which is actually more useful than ones complement, and we'll see what's going on there. The definition was r to the power of n minus the actual number. So it will be this 1 and 8 zeros minus the original number. Now, the same thing that we talked about before, everything needs to be borrowed, so we'll keep borrowing ones except this last one. So this will be a 2 minus 1, which is a 1. 1 minus 1, 0. 1 minus 0, 1. 1, 0, 0, 0, and 1. And that's the two's complement of the number. Not so much just inverting all the bits anymore, but almost. Because if you look back at the definition, the difference between the ones complement and the two's complement, so this expression here and this expression here, is that just that additional minus 1 that we have in the ones complement. And this gives us a very easy way to take the two's complement of a number. We can take the ones complement, which is just inverting all the bits, and then add 1, which we subtracted in the ones complement case. So going back to here, so this is, the long way of doing this. The quick way of doing this is to take the original number. I'll invert all the bits to begin with, so 1, 0, 0, 0, 1, 1, 0, 0. And then I'll add 1, so this is the ones complement. I'll add 1 to get the two's complement, which is the same thing as I got the long way. So whenever you're asked to take a two's complement of a number, and you will see, especially in the next lecture on Friday, that we will take tons of two's complement all the time, the easiest way to do it, invert all the bits, add 1. There's other ways to do it, by the way. You may have heard or you may hear about other ways. This is the method that I like. It works. If you prefer another method, go for it, as long as you get the right answer. So now I want to introduce the idea of doing subtraction using addition. So we've built the adder circuits before. We didn't quite talk about how to build subtraction circuits, but we sort of thought that they were very complex because we have to deal with which number is larger than the other. I do want to use my addition circuits to do the subtraction. And let's see how we can do it. And again, if you remember, what we're trying to do is m minus n. We'll start off with adding the 2's complement of n to the number m. So we end up with m plus, so we have an addition, the 2's complement of n. And we know how to take the 2's complement very, very easily. And because it's so easy, we can actually use this in hardware to take this 2's complement. We'll talk about how we actually do this in hardware on Friday. But now we reduce the problem to an addition problem. We have one term plus the other term. And this performs m minus n plus 2 to the power of n. So we're sort of already putting in the correction term in there. Now, if the case was that m is larger than n, and now remember we're doing addition, we will get a carry out from the adder. Because the number m minus n plus this 2 to the power of n will be too large for the number of bits we have, we will get a carry out. And this is if m is larger than n. Now, this carry out actually stands for the 2 to the power of n term. This is what we'll get in our sum. If we added it to the sum, then we'll get the correct answer plus 2 to the power of n. Therefore, if we get rid of this 2 to the power of n, we will just get the correct answer of m minus n. Who's confused? Try to think about it a little bit, even draw it, it all works. The bottom line here is that if we do get a carry out, that's a good sign. You just get rid of the carry out, but it means that the result that we got is correct. The other case, if n was larger than m, then this sum that we came up here will actually be in the right range, and we don't get a carry out. But this will tell us that the result is incorrect, so not getting a carry out is bad. And we have to apply the correction. And the correction is, just like before, taking the 2's complement of the number, or essentially do 2 to the power of n minus the result, and then stick a minus sign at the front, similar to what we've done at the very beginning a few slides ago. Let's have a look at examples, because doing things with m and m is not easy. So let's take two numbers, x and y, they're given up there. And we'll try to do x minus y, and then I'll try to do y minus x. And I will follow the algorithm just in the previous slide. The algorithm said we want to convert this subtraction problem into an addition problem. I will take the 2's complement of the second operand. In this case, if I want to do x minus y, I will take the 2's complement of y. And to prove to you taking the 2's complement is easy, it's going to be 0, inverting all the bits, plus 1. Which is what I've got here. And then I just do addition. Addition is really easy. 0 plus 1, 0 plus 0, 1 plus 1 is a 2. Carry a 1, 1 plus 1, 2, carry 1, 3 1s, 1, carry 1. 1 plus 1 is a 2, carry 1, 1 plus 1 is a 2. And then I have a carry coming out of this addition. We said carry is good. We got the carry out, meaning that result here is in fact correct. And we don't have to fix anything. Is this what your notes say as well, by the way? Yeah? Good. Because I've got notes from a few years ago that this was actually incorrect in my notes and I had to fix it. So I'm like, oh, is this correct? The other case, so we know that in this case then x was larger than y, all good. We'll try to do it the other way. So take x from y, we convert it into an addition problem. We take the 2's complement of x, invert all the bits, add 1, you end up with this. You just do an addition problem. And there's no carry coming outside. So no carry is bad, we want the carry. Meaning we have to correct for this sum there. To correct for the sum, we said we'll take the 2's complement of the result. So again, invert all the bits plus 1, and we'll stick a minus sign to that result. So invert all the bits, we'll get 0, 0, 1, 0, 0, 0, 0, plus 1, we get 1, 0, 0, 0, 1, 0, 0, and we'll add a minus sign at the front. And it's a good sign that this magnitude is equal to this magnitude and just negative in sign. So all the theory that I gave you, it comes down to this practice. And I think this is much easier to understand than to go back to the m's and n's and corrections and stuff. You just need to check whether you have a carry or not. And if you don't have a carry, just take the 2's complement and add a minus sign to it. I will say again, what we didn't talk about is how do we actually stick a minus sign in a digital design. On paper it's not a problem, you just put it up there. In digital design we only really have the 0's and the 1's. We need to find a way to actually put the minus sign there. Now what I will do, I will stop here for today. On Friday, I'll show you different ways to actually represent negative numbers in digital design. And we'll see which one's the best one, and we'll develop this further.